Go. Ian Hewitt from Oxford. Do it.
Thank you, Dave. Okay, so I apologise to the geologists who really want to hear only about magma. My talk is going to be nothing to do with magma really, but I want to try and draw some analogies with some of the behaviour in ice sheets, and I hope that given the equations that were explained this morning you can see what some of these analogies are, and I hope that you find it interesting if not useful. Please do interrupt. Dan has requested that if you do interrupt then you speak loudly so that everyone can hear, so please do interrupt boldly. I want to just thank, before I start, Christian Schoof and Richard Katz, who I've had lots of discussions about this stuff with, and I'm very grateful to them. I'm going to talk about, basically divide this talk up into two sections. The first one is going to be about modelling subglacial drainage systems, and hopefully you will see why I'm going to talk about that here. And then the second part will be about two-phase mechanics of temperate ice. This is more the direct analogy with the partially molten mantle. Okay, but the first thing I want to talk about is the drainage systems. The reason why you might care about this is to try and explain the flow patterns that we see in ice sheets. This is a picture of Antarctica with the colours showing the surface velocity of the ice that's measured using satellite, using interferometry. And you can see that the blue and pink regions are moving fast, the yellow and orange regions are moving slowly, and we don't completely understand why certain regions of the ice move much faster than other regions. This is a logarithmic scale. There's very large contrast in the speed at which the ice moves, and there are basically two sort of main reasons why we think that bits of the ice move fast. One is because they're lubricated underneath because of the presence of water, and the second is that there's just a viscosity contrast, so that some bits of the ice are much softer than others and they deform more easily. And those sort of tie into the two aspects of what I'm going to talk about here. So that's the sort of motivation. Little bit of background. So ice is a oh, you have a question?
Yeah, so how about driving forces?
Oh, you're left.
Driving, because those are parameters. So is
Okay.
it that is on a steeper slope or so, or I mean,
Okay, so the
should be some difference also in the driving force.
so the ground underneath here looks like this. The yellow is the elevation of the bed, and so there's a lot of mountain ranges and things. The main driving force that's making this ice spread out is the surface slope of the ice, which is determined by itself. That's not something that someone else determines. It's just spreading under its own weight, essentially. And there are some regions where you can explain fast ice flow simply because the ice surface slope is steep, but certainly not all of them. In fact, a lot of the very fast flowing regions are actually got a very shallow surface slope. The driving force is smaller there, but there's just so much less resistance that the ice moves faster. So that partly explains it, but not the whole thing. Yeah. So the ice deforms, and if you're modelling ice sheets, you generally treat it as a viscous fluid, where it's usually treated as a shear thinning fluid, and the viscosity depends upon temperature. And later on, I'm going to start talking about the viscosity depending on the water content when we're at the melting point. So this is going to be the epsilon dot is the strain rate, T is the temperature, and phi will be the porosity. We're dealing with very small inertia, so we're always solving Stokes flow when we're doing this. And if you try and model the flow of the ice, it's very important what you assume about what's going on at the base. And people usually assume some sort of friction law like this. So macroscopically, on the scale of an ice sheet, you can have slip at the base. So that's in this diagram here, that's just UV, I think, and that's because the ice can deform over obstacles on the bed, and I'll talk about that in a second. And so on the large scale, people generally try to model the ice flow with some sort of law like this, where the tangential shear stress is related to the velocity. This is a simple friction law, but the constant that goes in here, well, it's not necessarily a constant. It could certainly depend on space, and maybe depends on all sorts of things. And I'm going to talk about the fact that it depends upon the water pressure underneath the ice. So that's going to be the first part. The second part is going to be about the ice temperature, or the thermodynamics. And so the things that we'll have to worry about then are quite a lot of things, actually. These are all important in determining the temperature of an ice sheet. We have radiation at the surface, We have advection and conduction in the motion of the ice and in the heat conduction through it. Shear heating is very important because the ice is deforming. You have friction at the base, and you have geothermal heat flux from underneath, which is making it warm. And all of these things need to be worried about when you try and determine the temperature of the ice, and when you start worrying about it partially melting, which I'll do later on.
Can you just give us a hint now? Are any of these more important than others?
In some cases, so generally advection is more important than conduction, but not always. So the aspect ratio here is very thin. So conduction in the vertical is quite often comparable with advection in the horizontal. You see what I mean? Shear heating depends on how much the ice is deforming, whether that's important or not. I would argue that in the places that are interesting, this is important. Frictional heating is possibly not so important compared with the shear heating. Geothermal heat flux is actually not very important, except in getting the base of the ice to the melting point in the first place. Once it's there, it can then slide, and you get then enhanced shear heating, which is then the dominant factor. And the radiation budget on the surface is important sort of as a boundary condition. So there are some cases where they're not all important, certainly. I forgot to say, the whole of this talk is going to be much simpler in many ways than the stuff we've heard about before, because I'm going to assume that the ice is pure ice. There's only one component. I'm not going to worry about salt in this talk at all. And so that's going to simplify things a lot. Okay, so let me just motivate further looking at the subglacial drainage system. This is the friction law again, so the basal shear stress related to the basal velocity. There's lots of evidence which suggests that this depends upon the water pressure underneath the ice. And in fact, what's really important is a quantity that's usually called effective pressure, and is written as this N. And this is the difference between the hydrostatic ice pressure and the water pressure. So what really matters is what the water pressure is compared to the weight of the column of ice that's sitting on top. Okay, I'm imagining, so here's the water. It's not really a thin layer like this, but this is just a cartoon. We're interested in the water down here. We're under a big column of ice, and we want to care about what the water pressure is relative to the pressure in the ice column. Okay, this is another map of Antarctica. This is from an inverse method applied to an ice sheet model, where they have tried to fit what this beta number here is to observations of the surface velocity of the ice. And I don't know if you remember that the red colours here where beta is small, and these correspond very closely with the regions where the ice was moving fast. And the suggestion is that this corresponds to a small effective pressure. That's where the water pressure is very close to the ice pressure. This quantity is usually positive. It's going to turn out to be a bit like the compaction pressure that we've heard about this morning. But the idea is that areas where this is low will correspond to where there's less friction, and that helps the ice move fast. I don't want to get too much into the details of this, but there's a couple of theoretical reasons why we think that might be so, and that's what these cartoons down here are showing. One is that we think locally, zooming in close to the bed, the bed is rough, and you get separation of the ice as it flows over bumps. And the size of these cavities is controlled by this effective pressure, and that effectively controls how much the ice is in contact with the bed underneath, and then that controls how much stress is exerted by it. The other reason is that sometimes the ice is sitting on top of a layer of sediments which is saturated with water, and the pore pressure, or the effective pressure, controls the strength of those sediments. And so the deformation of the till underneath, it's called till, depends upon this effective pressure. Okay. For the purposes of this talk, all I care about is that we want to know how this effective pressure varies in space. And so that's the motivation for trying to model the subglacial drainage system, which is what I'm going to talk about now. So this is what the glaciologists think that it looks like underneath. This is a 3D picture of those little cavities which are forming as the ice flows over the bumps. They're connected together laterally, and the scale of these things is around about a meter or so. We're interested in kilometers or hundreds of kilometers scale. So I'm going to treat this sort of thing as being like a two-dimensional porous medium. And I'm going to try and model it as something
Can these things be
like this.
Can these regions of water be seen by any method, or is this all?
They can be. They have been seen by drilling into them through the ice. They have been seen by brave people crawling into them when they don't have water in them anymore. And they can be seen. I'll show you a picture in a second of a deglaciated bed where you can sort of make out where they are.
You can't see them with radar.
They're too small to be seen with radar. Yeah. Yeah.
I think you can actually see in the specularity of the radar. You can actually you don't see them as nicely as you want to, right? But you can see areas where there's more of those, right?
You can infer sort of wetness with radar through looking at the specularity, like you said. But you can't see the sort of pore structure as I imagine it here. Yeah. Okay.
And their lateral extent?
This is sort of meter scale in all dimensions, and they're not necessarily all connected together, but I'm going to imagine that they are. Yeah. So these are going to be sort of like poles in a porous medium. Okay. The interesting thing about this is that as water flows through these things, it loses potential energy, and that energy creates heat, and that heat causes the ice that's sitting on top to melt. So as the water flows through these things, it melts the ice that sits on top. And that can cause these passageways to enlarge in a fashion which is unstable. And so that can lead to this sort of cartoon picture where one of these pathways has become quite large and looks like a channel. And this is seen to happen when you get enough water flowing through this sort of system. Yeah.
What about air? If it drains and you leave a porous space?
Yeah, so the question is about air. So sometimes these things have got air inside them as well as water. Underneath the big ice sheets in Antarctica, it's very unlikely that there's any air down there. It will all be water filled. But not impossible. Yeah, then we'd have to worry about it being unsaturated, and that's a whole extra issue to deal with. I'm not going to talk about. Okay, this type of situation, we haven't found a good way to describe this in an average sense. You can think about sort of dual permeability models, sort of fracture-based models, but the interesting thing about these channels is that they change size quite dynamically. And so the sort of models that we've gone to try and model this is a sort of hybrid where we imagine individual conduits which we describe in a discrete sense interacting with a porous medium on the outside, and I'll talk about that after I've talked about this one. This is just a picture showing a deglaciated bed in Canada. This is a zoom in on this region. Here you can see these sort of bumpy beds, and you can sort of imagine the water flowing between these bumps. This is a picture of quite a dramatic one of these channels that the water has melted this big shape. This one happened in a big flood, which is why it's so circular. They're not always so circular, but you see these a lot. Okay, so going towards trying to construct a model. So I want to try and describe this picture in this sort of cartoon framework, and so I'm trying to conserve mass of water here. So this is a conservation equation for water. Q is going to be the flux that flows through these things, and I write down a law that looks a bit like Darcy's law. H, you can imagine here is the average water depth, but you can think of it a bit like a porosity. The source terms on the right hand side here, there's two. M is the local melting rate. That's water which is created by locally melting the ice. R is water which has come from somewhere else, and I'm here thinking of water that's come from the surface of the ice, going down through cracks in the ice, through crevasses or moulins, which are shafts that take the water to the bed. So that this one is, for my purposes here, prescribed. And it might be point sources, it might be distributed everywhere. But that's the main source of water here. And then there's going to be a little bit of local melting. The direction that the water flows in, this phi thing, is a gravitational potential, and so it includes the height of the bed, that's what the water is flowing along. This is this picture down here. And the water pressure, and then I'm writing the water pressure in terms of this effective pressure. And so here I've substituted in the ice pressure, the pressure due to the weight of the column of ice. And you get an equation that's like this. All of this stuff is just the geometry, and basically the direction that the water flows in will be determined by the surface slope of the ice. That's that first term, with a correction due to the gradients of this effective pressure. Okay. There's two things I haven't done. Well, the first one is to write down how I determine H. So I'm going to write down on the next slide an equation to determine how H changes in time. That's going to be like changing the size of the pores. And then the other thing is this melting rate. I need to determine that through energy conservation. And so here's my equation for this H. So I'm writing down, this is a sort of phenomenological thing. I'm just writing this down based on how I think the individual cavities here will evolve in time. And there are three components to this. The first one is melting. So I'm going to melt the ice. And then the second term is the fact that the ice is sliding over this bump. And that makes the cavity get bigger. And so that's what this term is. This is just a parameterization which has got the right behavior. UB is the speed that the ice is moving at. And then this term here represents creek closure. So this is the fact that here the pressure difference between the far field out here, which is at the hydrostatic ice pressure, and the water pressure in here, that's this effective pressure, and that drives the ice to creep inwards. And that's what this term here is. This is like a compaction term in the equations that we heard about this morning. The melting rate is determined by a local energy balance, and I won't go into this too much, but there's geothermal heat, there's heat conducted upwards into the ice, there's frictional heat, and then this term here is quite important. This is the one which represents the heat which is dissipated by the water flow. So this one is coming from the water flow, and L is the latent heat. So this is just an energy balance to tell me how much will melt. I put that equation.
You don't have any energy contribution by the water draining down from the surface.
So that's going to be included in here. So the fact that you imagine that the water's draining down through, say, a kilometre of ice, and that loses a lot of, well, that gives you a lot of potential energy, but that's all encompassed in this term, because this term represents the dissipation of that energy. So it's all included in there. So the magnitude of Q will be determined by how much is coming from the surface.
So the evolutionary law, it is something what you observe from the data, how you introduce it, just by intuition?
So this is based partly upon what people have observed when they have crawled inside these things, but only qualitatively, not quantitatively, and then partly based on small-scale numerical simulations of this situation, right, taking into account, trying to understand how these things change size.
Okay.
So these come together with two equations I wrote down before: mass conservation and this potential. This psi thing just represents the gradients of the surface slope, which are driving the flow, and then the n is the effective pressure. The way that I think about these equations is to say, it's a bit peculiar because I've got two dHdt's. I stick this one into here, and so this equation is really a elliptic equation for the effective pressure. Right? The effective pressure is here and it's here, and this is a bit like the equations that we talked about this morning. You get a sort of modified Helmholtz type equation for the effective pressure, and then you think of this one as being an evolution equation for H, equivalent to an evolution equation for the porosity.
HR is greater than H or smaller?
HR is always larger than H. Yeah, this term is always positive. Okay, so the interesting thing about this comes from this term, which I think of as a sort of reaction term. The Q in here is this term here, and this K of H is a permeability function which increases with H. So this term is increasing in H, and it's generally increasing with a power which is larger than 1. So if I look at this equation and think about it in isolation, it looks something like this. So this term is that dissipation of energy. This term is the creek closure term. I put in the power law viscosity dependence on the ice in here, but it doesn't matter too much. And then this term is just everything else. And the important thing here is that this function, if you draw it as a function of h, looks something like this. And so you have, if h is small, you can have a steady state, which is stable. If h is larger, you get to this steady state, which is unstable. And that's because this term, if I increase h a bit, this term takes off and causes h to increase more and more. This is the runaway melting of the roofs of these little cavities. And if you try and solve these equations, what you will find is that you get h grows and grows and grows in a narrowing region, similar to some of the things that you see if you solve reactive infiltration instability. And you find that in this case h is not a porosity, so there's no problem with it getting larger than 1. It just gets bigger and bigger in a narrowing region. Yeah.
So if h becomes relatively large, you might start to have inertia too, right?
That's true. So yes. So I've ignored any inertia in the waterfall. I think you'd.
That will change the functional form of that shape as well.
Yes, it could potentially. I don't think that that's a big issue, but it might be something to think about. Yeah. So the way that I'm actually going to get around this, so this is a problem if you're trying to write down a continuum model and it starts localizing on basically whatever grid scale you're using. So the way I get around this is to say, okay, I'm just going to ignore this term. And I'm just going to neglect that, and I'm going to deal with that completely separately. And this is where this idea of having a porous medium interacting with individual conduits is going to come in. This instability represents the growth of these channels, and so I'm going to deal with those completely separately.
Ian,
Yeah.
Following up a little bit on the question about it getting some inertial terms in it. I mean, if your pores are getting significantly large, you may wind up having more turbulent Darcy drag.
Yes.
Standard laminar Darcy drag, which is
Yes.
A nonlinear function of your separation velocity. So
yes, and that's
that could have a big effect. We see it in volcanic flows, certainly.
okay. Wait 2 seconds. Sorry.
I'll ask again in 2 seconds.
Here is my model for how a conduit works. And so this is a conduit, and S is going to be the cross section of this conduit. And so I'm going to write down very similar laws here. Mass conservation is here, and then my flux law is now a representation of turbulent drag, because I'm assuming that these things are big enough that the flow in here is turbulent. So this is where this the gradient here is to the power of a half, which is what you typically get out of these turbulent drag descriptions. So I'm kind of assuming that somewhere between that pore scale and this scale, I've transitioned to turbulent flow. And so that's where this is going to come in. So in this equation, so Q is the flux through this thing, M is again the local melting rate, that's the melting rate at the walls of this thing, and Q in is the flow which is coming from the sides, that's coming out of these pores that are in the neighboring regions. And so it's still driven by this hydraulic potential. And then we have to write down a similar equation that describes how the size of these things changes. And here we include the melting rate, and we include this creep closure thing again. That's the two things that are in there. Okay, and this melting rate is now determined, got two components. One is the heat which is dissipated by the flow through this channel. So that's this term. And then this term is a slight fudge, but this is the term that I just said I was going to ignore. This is the term which is the heat which is generated by the flow through the pores. And now the reason I call it a fudge is because the heat which is generated by the flow through the pores is somewhere out here, not in here. But I'm going to just try and lump that together and say the reason why this thing is growing is because of that heat, and I want to try and include it somewhere, so I'm going to stick it into here. And this is what makes this conduit start to grow in the first place. So there's an issue about what that lambda c is, which I won't get into. Okay, so this is how these conduits will behave, and you can look at a similar sort of thing. This thing doesn't even have the small f stable steady state. It's always unstable. If I just look at this equation, that's not a sensible thing to do though, because What's actually going on here is that we're constrained by the total amount of water flow, which really controls what this N is. And so what you find is that you don't get these things growing without bound because you're constrained by the total flow. But what you do find is that if you had two neighboring channels, then they'll compete with each other, and the larger one will suck the water out of the smaller one within some distance. This is the sort of hybrid model that we've been using. So this is the sort of porous region out here described by this H thing, and then a channel which I sort of imagine sitting on top, although that's not really what's going on. And the model that we've developed for trying to describe this uses a finite element mesh where we end up saying that the channels will reside along the edges of the mesh that we're using to solve for this H, which is a continuum variable and is defined everywhere. And so we developed a numerical method to try and solve for these coupled equations. I'm not going to write out all of the equations, it's basically everything that you've seen so far. And we try and solve for what the water pressure is. And this is just an example. I'm not really going to show any results here, I'm just looking at the equations basically, but you can maybe make out here, I don't know if you can see all the colours, this is, you can see the mesh here. This is quite coarse resolution. I think there's something like 10,000 edges here, and this is going through time. If you start off with a sort of uniform state, there's a uniform source of water here. Imagine coming from here, sort of raining down everywhere, and the flow is from left to right. So you collect in water as you go down the glacier, which is going to the right, and over time you find that these things sort of compete with each other, as I was saying, and they localize into this sort of pattern. The spacing between these things ends up being controlled by something which is equivalent to the compaction length in the equations that we talked about this morning. But these things are individual channels, but they're solved as being individual channels, which stops them getting too big, because effectively you're resolving the size of them, the area of them.
Are these those enclosures you showed in the beginning? Because there you said those have dimensions of a meter in all directions. Whereas here you're saying they are a channel.
They're elongated, yes. Sorry, let me just quickly go back to the cartoon.
Yeah.
So these things are sort of a meter in all dimensions, but that's ignoring the connections between them. Then this thing is when the connections have joined together. So these things are joining together and making a long string of themselves.
And the competition between them, the way it's distributed, is because of just the size, or other things different among them, like the roughness of the bed, or
I've assumed in the solution that I just showed you that the roughness of the bed was uniform. So all of the sort of funny routes that the thing was taking is generated by the randomness of the mesh that we're using to solve the thing on. So you have to be a bit careful with these sorts of things, that a lot of the solution will depend upon the mesh because we're explicitly solving it on a mesh. And so you really want to do statistics to see some of these things. Okay, let me go on to the second part of the talk, which is about temperate ice. So this is changing tack slightly. First, just a word about the temperature of an ice sheet or a glacier. If you look at many alpine glaciers that you go skiing on, they're mostly temperate, and by temperate I mean that they're at the melting point. And so that they're in equilibrium. The melting point will depend upon the pressure, although actually I'm going to, for most of this talk, ignore the pressure dependence. It's important for some things in an ice sheet, but not for what I'm going to talk about. If you go to higher latitudes, you find that most of the glaciers are what is termed polythermal, meaning that some of the ice is below the melting point and some of it's at the melting point, and that's shown here. So the grey bits are temperate, that's at the melting point, therefore containing some water. Interestingly, you often find that the temperate region is actually the bit high up, which is slightly counterintuitive. That's where the air is colder, and the reason for that is that up here the top of the ice is covered with snowpack, And so when you melt in the summer, the water that's created stays in the snowpack and doesn't run off, and then refreezes. And when it refreezes, it produces a huge amount of latent heat. And so you actually get the top of the region up here is warmer than the region down here, where as soon as the ice melts, it runs off, and that latent heat is lost. So you can get some slightly counterintuitive temperature patterns in these ice sheets. If you go to the bit large ice sheets, it's cold enough on the surface that the surface ice near the surface is definitely cold, but you can have it be locally temperate near the base in some regions. And so there are some places where they've drilled into the edges of the ice streams in Greenland. They found up to about 50 meters of ice at the base, which is temperate and containing small amounts of water. The amount of water that it contains is usually less than 1% volume fraction. And so there's quite a bit of history of trying to model these things, which I'll very quickly summarize. There's a few papers early on which concentrated on trying to understand the crystalline structure of the ice, and particularly whether it was permeable. And the conclusion of that was basically that this is very like silicate melts in the mantle, in that this is a picture of the pore structure. The water is contained in triple grain intersections and full grain intersections, something like this. And the dihedral angle is very small, so we'd expect, or not very small, but small. And so we'd expect that the ice is permeable, even at very low melt fractions. The reason why people care about the melt fraction of the ice is because the viscosity depends upon it. And some of the early models tried to write down continuum formulations for how to describe the temperature in the temperate ice. Well, no, not just the temperature, but the water content. And the early models assumed that the water didn't move. So they just had it been advected with the ice. And I'll summarize that in a second. There are then two major papers which were developed sort of at the same time as a lot of this stuff was going on in the magma literature. And so this is by Columbine Hutter and Andrew Fowler, who both wrote down sort of two-phase flow theories and made different assumptions about how the water was going to move through the pores. And basically what I'm going to show you here is building on these, and doesn't do an awful lot more. They had quite a bit of confusion about what the boundary conditions were, which I hope I've now resolved, but I'm not going to go too much into the detail of that. Later papers have tried to compute things. These basically follow this formulation back here, where they don't worry too much about how the water moves through the ice. What they do is they let the water content of the ice build up, and then when it gets too large, they just cap it, and they just say, can't get any higher than that, and they sort of have to abandon energy conservation when you do that. But that's they try to do that in a sensible way, in as much as abandoning it is sensible. As a starting point for trying to understand the equation for temperate ice, this is a quick summary of how you model cold ice. Okay, so we're dealing with Stokes flow, temperature dependent viscosity, and you have an energy equation that looks something like this. So this term here is the shear heating term, which is where a lot of the heat's coming from, and then the geothermal heat flux and everything is giving you the boundary conditions for solving the temperature on a domain that looks something like that. So that's the sort of starting point. When we go to looking at polythermal ice, I'm first going to look at the case where there's no movement of the moisture away through the matrix of the solid ice. And so the changes that we need, let me just flip back. So I've changed. The viscosity is now a function of the porosity, and the energy equation now has to have two parts. One, when the temperature is below the melting temperature and the porosity is 0, and then another one when you're at the melting temperature, which I will assume here is just a constant, so no pressure dependence, and then the melt fraction is larger than 0, and you just convert your energy equation from being an equation with temperature to being an equation for the water content. L again is the latent heat. You've still got the shear heating term here, which is what gives rise to the increase in the porosity. Typically, you try and combine these two in terms of an enthalpy. So I define an enthalpy like this, and then you can write these two in this form here, where you just have different types of flux terms depending on whether you're temperate or you're temperate. So this is cold or temperate. And here I've just added a regularization term, which is typically what people do. So you add a very small amount of diffusive heat flux in the temperate region. So this nu is very small. And I'll just quickly show you what solving something like that looks like. This is a model ice sheet. The black lines are streamlines. So the ice is forming up here and then melting down here, and it spreads out sideways. The red colouring behind is the dissipation term. That's the shear heating term, which is largest down here where the shear is largest. And then it gives rise to these temperate regions, which are what these blue regions down here are showing. This is the solution for the temperature and for the porosity, according to that model I just showed you. And so here you can see the streamlines again. It gets warmer as it comes down because it's getting heated up. At some point it becomes temperate, and then you very quickly saturate the color bar here. So there's a very little white bit in here where phi is sort of less than 1%, and then it becomes blue. And in fact, the porosities in here have gone up to something like 20%. And you carry this up almost to the surface again, and then it refreezes just before it comes up out at the surface. This is not what we think happens, because we think that the water should really drain, but I neglected that from this model. So here's coming back to the equations again, but now with some moisture movement. So I modify the equations a little bit, and this is very similar to some of the stuff we heard about this morning. This J term is a Darcy velocity. So this is like phi times the velocity difference between the water and the ice. And so mass conservation looks something like this. This is with a Boussinesq approximation, so there's no density difference term for the phase change. There should really be a change in this equation, which you want to think of as the overall momentum balance. But because the porosities we don't think are going to get very large, the overall momentum balance is still completely dominated by the solid phase on its own, and so that's this one. And the energy equation just gets this extra term here, which is the divergence of the heat flux carried by the pore fluid flow. That's this J term there. And so this is not complete, because you've got to say something about what J is. So that's the next part. So I just rewritten that equation in terms of the enthalpy again, and so there's this J in here. I've got to decide what that is. So I'm going to use Darcy's law, like this. And then I'm going to decompose this pressure in lots of terms. This is very similar to what we saw this morning, what Mark was talking about. So this is the pore pressure. I'm going to write it as a lithostatic pressure, or cryostatic in this case, plus a what I call a reduced pressure, but you could call it a dynamic pressure. That's the rest of the solid phase pressure, an effective pressure, and a surface energy term, or a surface force term. Right? And so this is a little bit complicated. There's an awful lot of different pressures in there. But I guess maybe the interesting one is this effective pressure, which I'm then going to relate to the rate of viscous compaction. And this is the same as you do in the magma equations. Okay, eta over phi is like the bulk viscosity. Okay, and then so we substitute that back into Darcy's law, which now looks something like this with all of these grad p's. There's then two different approximations that I make. One is where I think that this term is really important, and I ignore this term. And the other is where I think that this term is really important, and I ignore this term. These are two options. And which one is right depends on what we think the size of the grains is, and what we think that the surface energy is. I'm not going to write down what it is, because I don't know what it is.
You're just going to ignore it.
Either I'm going to ignore it, or I'm going to assume you'll see in a second. I'm going to assume it's something convenient. Yeah.
The last equation is J, Darcy velocity?
J is the Darcy
The last
velocity.
equation.
In here, yes. Yes. So this term here is really minus the divergence of u, which was the solid velocity. And then using mass conservation, that's the same as the divergence of j.
Okay, so you put that in that equation.
So I stick this into here, and then this is what again gives me this sort of Helmholtz equation for PE. Right, I stick this into here. Everything in here is sort of known. At least you should think it's known. And then so this is then an equation for PE. And yeah, it's the same equation again. Yeah. Okay, so these are the two. So there's two alternatives that I'm going to use here. This is going back to the equations before. I'm going to use either this version, where I ignore that PS term. So this is what I call a compaction model, and so that then I combine these two terms to work out what PE is. You only have to solve these, of course, in the region where phi is non-zero, in the temperate region. And then once you've solved this, you kind of know what J is, so you can put it into here. And then the other version is where, let me go backwards, I ignore the PE term and keep this term. PS is a function of phi, so I can write this in terms of a gradient of phi. And with a bit of wishful thinking, I can say that J will look like this thing, plus a diffusive term, where the diffusion coefficient is given by this thing, and I hope that that's a constant.
Why don't you keep both terms?
I could keep both terms. You could keep both terms. I just wanted to give two simple versions of the model that come in either limit. It's perfectly possible to keep both terms. Yeah. I mean, in reality, I think that, well, both may be important in different situations, but most of the time one of them will dominate. It's only for the purposes of the example solutions that I'll show. Okay, so there's these two models. The only other thing that I just did, going from one side to another, was to say I'm going to ignore the divergence of J term that was there. So that term is small, at least in the context of ice flow. So I'm going to assume that the ice is approximately incompressible. This is a little bit like what Mark was doing this morning. So this bit is really the compressible part.
So you've just taken PS and you've written it as dps, d phi, dx.
Yes.
So it's just grad p.
This term came from phi squared times grad ps, and then because ps is a function of phi, by the chain rule I just write it like this. And there's no particularly good reason to think that this will be a constant, but so the ps dependence on phi depends on the detailed structure of the pores and the surface energy. So I don't particularly want to get into what exactly I think it is. But I mean, it's quite reasonable to think that PS might look like 1 on phi. So this PS over phi might look like 1 on phi squared, and so conveniently they cancel out.
You're trying to get a diffusion term in here.
I just want a diffusion term, and since I don't know what it is, I might as well make it linear. Okay, so there's a couple of example solutions that we've looked at to try and understand how these equations will behave, and these are a little bit like the upwelling column models that you see in the mantle. So this is a parallel-sided glacier. Here's the bed. Here's the surface. There's this shear profile in the ice. I'm going to assume that the surface is at some fixed temperature and that the base is at the melting temperature, and this shearing is giving rise to heating inside the ice, and that's going to cause a region near the bed to be temperate and have a non-zero porosity. To make it interesting, I'm going to assume that in addition to this parallel flow, there is a vertical flow, either downwards or upwards, and I'm not going to worry about the fact that this means that ice is going into the bed or coming out of the bed. Because this is
actually the solid velocity, or
this is the solid velocity. Yeah. So in the context of an ice sheet, the bits in the middle where the ice is accumulating have a downward component of vertical velocity, and the bits near the edge where the surface is melting have an upwards one. So you can sort of think of these as being like different bits of the ice sheet. And so this is a nice example because you can construct some of the solutions just analytically. It's all one-dimensional. So this is a solution if I don't have any water transport. So that J term is just 0 if you cross it out. And so the solution looks something like this. This is the temperature. It's cold up there, gets warmer, and then you end up with this region down here. I don't know if you can see the shading, but there's supposed to be a shaded region down here, which is the temperate region, and the porosity increases in there as going down. There's no movement of the water here other than advection, and because the thing is moving downwards, this arrow is showing that the solid is moving downwards, the porosity is being carried out the bottom. If it were not carried down, then there would be no steady state here. I would just be constantly generating porosity in the bottom layer. If I turn it round and have the ice moving upwards, you get a solution that looks like this, where so now we're advecting out of the bottom stuff that's at the melting point. So we get a much larger temperate region. So all of this bit's now melting. The porosity increases as you go up, and then you get a very cold region at the top. You get a discontinuity in temperature flux here because all of this water that's in the ice suddenly freezes, and that does so at a particular position there. Okay, so these solutions you just get analytically. If you now put in the moisture transport, you get something slightly different, and that's what's shown here. And all the different colours here are different models. And both of the two that I showed you before are shown here. Annoyingly, I haven't labelled them properly. So this is the situation where the ice was moving down, and they all more or less give you the same behaviour. In here, the porosity is a little bit different for each model because the water is now draining down. So the water was being advected down. It's now, in addition, falling under gravity through the ice. And so that means that you generally end up with a lower porosity than we had before, although this is all a bit scrunched up at the bottom of this picture, so you can't see it very well. You get a much bigger difference in the case where the ice was moving up, because now gravity is trying to pull the water. So remember, the water is more dense, right? So the gravity wants to make it go down. This is all upside down compared to the mantle. So the water wants to go down. It's going against the way that it's being advected, and so depending on what you assume, you get quite different amounts of temperate ice here. So the orange one here is what I call standard enthalpy gradient model. This is just a diffusive approximation to the one that had no water movement. So you just get a smoothed out version of that jump. The blue one is the compaction model. So in this case, the water is draining, and you get this profile of porosity, which I'll talk about in a second. The pink one is the other one where I had the PS term, which is a diffusive regularization of one where you only have gravity-driven flow. And the gravity-driven flow is pulling the water down, and you get that pink profile from that one.
And you're forcing the porosity to be 1% at the bottom as an inflow?
Yes, right. So in this case, yeah, we've got an inflow, so the porosity is prescribed at the bottom. Yeah. Yeah. Now, the interesting part about this, I'm nearly done. So the interesting part about this is this compaction pressure model gives you these large porosities, which have gone off the scale here, and this blue one, and that's because we've input the porosity at the bottom. You need a large effective pressure gradient to try and drive out all of the flow, all of the water which is being produced above, and you get these quite interesting patterns of large and then small porosity. If I change the parameters slightly, you can get sort of multiple porosity waves here, but these are static porosity waves. This is a steady state. This is a steady state solution.
You're against the counterflow.
And it's because so in this case we've got advection going that way and gravity pulling it this way, and you can effectively make the porosity waves get stuck. Yeah. If you make this porosity down here much lower, you find that the steady state disappears completely, and we run into problems then. we think that what happens in that case is that you just get large bands, and then in reality what happens is that the water will then flow sideways, because here I've assumed it's one-dimensional, but we're not quite sure. So that's what's going on there. This is just to go back to this example that I showed you before, and just want to show you the difference in the solutions. This is the solution that you saw before, where you get this large amount of water down here. This is with the compaction pressure model, where the water now drains out. So the pink lines here are the streamlines of the water flow, the white ones are the streamlines of the solid ice flow, and so the water is now all draining out underneath.
Is that shown with the real aspect ratio, or is it exaggerated?
Sorry, that was exaggerated aspect ratio. Yeah, this is way taller. This is actually small, thin. Yeah, this is. Yeah, the ice doesn't really go sort of up like that. There's not like sort of fountains of ice coming out of the bottom of Antarctica.
It's like 200 meters by 200 kilometers or something.
Yeah. The aspect ratio here is changed by at least 100. Yeah.
And you don't have a feedback with viscosity here, so you haven't then changed the structure of the ice yet.
No, thank you. In this, the solid flow I've just prescribed, but I haven't put the feedback of the viscosity into here. That's the next step, which I haven't done. Yeah. But obviously the point of this is that these regions here where there's water are now weaker, or at least we think that they'll be weaker, and so they lead to enhanced shearing here, and then that will actually just change the shape of the ice sheet and lead to, well, you have to go a bit further with studying this. The last thing I wanted to say was something a bit different that I don't really know anything about, but I thought I'd just point it out because this is another use of these compaction equations. If you go to Europa, one of the moons of Jupiter, that has an icy shell sitting on top of a water ocean. The ice is something like 30 kilometers thick, and people believe that it's convecting. It's cold on the surface and warm inside. So the ice is convecting, and as it convects, it partially melts. At least so the claim is. So people have used very similar equations to try and understand the melt that's produced in the icy shell. And so this is a simulation of temperature and porosity through the depth. So this is time going from left to right. This is the depth, and this is with some different parameter values. And you find that you get this water. This is the porosity, and then it drains, and you get what's claimed to be porosity waves in here as well. But as I say, I don't know anything about it. I just wanted to point it out as another interesting application of what's effectively the same equations. Okay, I've reached the end. In my summary, subglacial drainage systems exhibit some behavior which is quite similar to what we've seen here. It's much simpler in many ways because of the lack of any components. But you see compaction, you see porosity waves in the subglacial drainage system. I didn't really talk about that, but you do get that. You get this reactive feedback giving channelization that's completely run away to make completely pure water-filled channels. Partially molten ice has got porosity weakening viscosity that may be quite important, and that these equations are useful for trying to understand some of the feedbacks that might lead to. I'll be very happy to take any more questions. Thank you for your attention.
Questions? I will run around with this microphone. If you're not loud enough, I'll hit you with it.
One second, that question I have in
Maybe I missed it, but did you make comparison of your model with the ice sheets on the South Pole, because you had those with different velocities and in different areas?
No, you didn't miss it. I haven't compared it because I haven't got so far as to try and compute what the velocities are as a response to what I've done here in computing the temperature and the porosity profiles.
But do you think you can explain now some of those huge differences?
Not yet.
I can show
It's okay.
Make it loud.
Really. I wondered if are there any circumstances under which you think that the movement, the transport, and the deposition of sediment is important in controlling the development and evolution of the channels?
Yes, I think that probably is important quite often. So we're dealing here with ice down near the base. So all of the temperate bits of the ice are somewhere down here, and in fact this base is not flat, it's really mountainous, and this is where the pressure dependence does start to come in. The pressure dependence down here leads to sort of both compressional melting and decompressional freezing, and so this is another thing that's the other way around compared to the mantle. So when the water down here is flowing up mountains, which it does, driven by the surface slope, it will refreeze, and when it does that, it will entrain a lot of sediments. So actually, this basal ice down here is probably very dirty, and that means, yes, that it will affect the production of these channels, and also it will start to mess up the thermodynamics and mean that we do need to worry about other components altering the clean picture of the phase diagram that I talked about here. Well, I didn't have a phase diagram.
A question right here.
Just that I have an idea how strong is the effect on the viscosity. How does it compare with the decrease in viscosity you get because you get a preferred orientation of the ice crystals close to the base? That's the other way of weakening the basal ice.
So the honest answer is that I don't know. I think that both of them are likely to have more important effects in different locations. So I think the rearrangement of the grains and the fact that you get anisotropic viscosity is certainly important in some cases, and will probably be much more important than any presence of water. So what the experiments that they've done have shown that if you get about 1% water content, you change the viscosity by a factor of 10, and you can get similar changes and even more through reorientation of the crystal.
Okay, thank you.
Well, speak loudly until I get to you.
Are you completely confident that ignoring the pressure dependence of the melting point is safe? Because it looks to me like you had a temperature gradient of about 1 degree over 200 meters, which is about 20 bars, which would lower the melting point by about 1/6 of a degree. So it's small, but it's not negligible in terms of correcting your energy budget.
So
did you all hear that?
So the question was about whether it's safe to ignore the pressure dependence. So to be honest, you can include the pressure dependence here, and I only ignored it to keep the presentation simple. The change in the results that you see here would be small. Obviously, when you see these pictures of like here, the temperature is 0, it won't be 0 anymore, it'll have a slope. But the effect on the porosity will be small. So the amount of heat that's gone into producing this, you don't need very much of that to account for the pressure change here. But definitely there are some cases, particularly if you're worried about these very mountainous regions underneath Antarctica, where you do need to account for the pressure dependence. But it's not difficult to do that. Here, I just ignored it for simplicity.
Any more questions?
Actually, so if there are no more questions, I will say one thing on that. Which is that, so it's easy to include it if you assume that the thermodynamic pressure is the ice pressure, the solid pressure. If you assume it's the pore pressure, the fluid pressure, you get some wacky things going on, which we haven't yet understood.
Okay. No more questions? All right. John, what's our
C.
C.